so I guess it's about time to start. We'll see if James is actually online, but we had some technical difficulties. So we have quite a few people here. So we have Simon, we have Daniel, we have John, we have Laurent, we have Jason, we have Alex, and we have James, who's going to present. And the stage is yours, folks.
Okay, so it seems like James is trying to join again.
Yeah, when I present, it starts freezing. Of course, only now. Still there?
Yeah,
yep,
we can see it now.
We'll see how long that lasts. Okay. Welcome to the XDC 2020 version of the Allocation Constraints talk. I'm James Jones. I work at NVIDIA on the Linux graphics driver. I've been working on Unix device memory allocation problems for several years now.
Yeah, hi, I'm Simon Sir. Oh no, James just disconnected, it seems. Or was it the old James? Oh, okay, never mind. Okay, so I'm Simon Sir. I've been working on Wayland for quite some time. I'm working at SourceRoot, and I'm pretty interested in fixing the allocation constraint issues. So I've been working with James for this this year's edition. Yeah. So let's first begin with describing what we are trying which problem we are trying to solve. So hardware can do everything with any buffer. So there are some hardware limitations that make it so you can't just allocate any buffer and use it for anything. For if you want to display a buffer, there are some restrictions. If you want to render to a buffer with a GPU, there are some restrictions. So all of these hardware limitations depend how the hardware is used. So the set of limitations to display something in any NVIDIA GPU will be different from the set of restrictions that the buffer must satisfy to render something. Historically, the driver have been accounting for this internally. Nowadays, a lot of setups have multiple devices involved. There are multiple examples of this. For instance, you have SOCs with split display and render engines. There are also some laptops with integrated GPUs and discrete GPUs that you want to share buffer between them. You may want to do a bunch of stuff like displaying, rendering, using video hardware acceleration, and with the decoded videos, for instance, process them in the GPU and then display them. So all kinds of things. So the problem is basically we have multiple drivers. Each driver is not aware of other devices' limitations. How do we make everyone agree? How do we allocate a buffer that can be used on multiple drivers at the same time?
Okay, let's start off by going through some definitions of the terms we're going to discuss in this presentation. The most basic one is a constraint, which is a single atomic definition of one limitation of a device or engine that's trying to access memory in some way. So examples of a constraint would be any kind of address or pitch alignment requirements, a maximum buffer size or pitch, locality, like if memory has to be allocated on a chip that's physically near to the device in question or actually on the device. Contiguity, meaning the device can't access something like a scatter-gather list. It doesn't have virtual memory capabilities. It has to operate only on contiguous pages. And then some kind of baked placement or interleaving, where you might need individual pages, bytes, or even bits to be placed in individual banks to get the required performance or the required properties. Constraints are atomic and self-contained. That is, the individual constraints don't rely on other constraints to be fully expressed. They stand alone, and you can operate on them independently of each other. And constraints can be mergeable. So if you have something like a pitch alignment requirement, and you have two different ones, you have, say, a pitch alignment of 4 bytes and pitch alignment of 6 bytes. If you merge those, you take the least common multiple and get a pitch alignment of 12 bytes, which covers both use cases. Usage is a description of what operations are going to be performed on the memory for a given engine or device. So some examples of usage are a pixel format or a textile format. Operations like texturing or rendering, video encoding, decoding, or capture are using a display, for example, displaying at one particular resolution and at a particular rotation setting. And the granularity at which you express these might vary depending on which API or driver or mechanism you're using, but to some degree you'll have to propose some usage for the device so it can report to you constraints. A constraint set is a list of individual constraints imposed on memory for a given usage. So for any given usage you propose, a device has to be able to report to you all the constraints that apply for that device for that usage. And so we call that a constraint set. Like constraints, constraint sets can be merged. And the most useful property of that merging is that when you merge multiple sets, you get something that describes the constraints that apply to the union of all the usages that you specified when querying those sets. So if you asked a display device what its constraints were, and a rendering device what its constraints were, and then you merge those, the result would be something that expresses all constraints that apply to both displaying and rendering. Another property that's useful is that when you merge constraint sets, it does not in itself produce new constraints. So if you have constraint set A and constraint set B, and you merge both of those, the resulting set won't be any longer than the length of those first two sets combined. And right here is a small example illustrating what a merge operation applied to a constraint set looks like. So you see there's a simple constraint set that only has one constraint, a surface alignment requirement. Then there's a second constraint set that has both pitch alignment and surface alignment requirements. When you merge those, you take constraints of the same type and merge them individually, producing one new constraint. And if there are constraints that exist only in one list, you just concatenate them to the new list. So you see the result there in the diagram.
Yeah, so this year's edition is a little bit different from the previous editions in multiple ways because the landscape has changed a little, modifiers have happened. So this proposal strives to integrate with the existing ecosystem. That means integrate with APIs such as OpenGL, Vulkan, KMS, GBM, video for Linux, maybe VA API, and so on and so forth. We designed our proposal to be extensible so that we can have a proposal of just a minimum viable product, and then extend the proposal as we go. And if a new driver comes in with new hardware with different requirements, we can just add new features to the mechanism and extend it like this. We focused only on constraint resolution alone, so different but related problems such as trying to pick which allocator to use, we haven't addressed these issues. Other issues like I/O, MMU, discovery, or programming are not addressed. It's already a big task to do only constraint resolution.
Definitely. So trying to address those design goals, start out with a high-level design proposal, then drill down from there. Sort of talking about how we came up with the design we did, and then how we got to a low-level proposal at the end. So at a high level, like we said, we wanted to leverage existing APIs. So we use the existing API mechanisms to describe usage. So that means things like bulk and image properties for image creation. The existing like EGL image mechanisms where you specify a DRM format or other OpenGL texture format parameters, and DRM-KMS planes for display, specifically planes, and then how also all the parameters you specify at mode set time as well. You query constraints from an existing API given a piece of usage or a description of the usage you want to use. So this is similar to how format modifiers are queried now. And then the one difference there is that constraints are reported separately for every given layout that you use or every given format modifier. So if you queried 5 format modifiers already after specifying your usage, then you have to, for each of those format modifiers, again query a constraint set. So you end up with this kind of combinatorial level of data. So there is a lot of data here for the application to manage. We'll provide logic to merge constraint sets in some common code. This is the main operation you need to perform, but it's the same for any component using this mechanism. So hopefully we don't have to write it more than once. And after you've merged your constraint sets from all your different devices and usage, you can pass them on down to an allocation API of your choice at allocation time. And it shouldn't really matter which allocator you use, as long as you pass in the right constraints, it should be able to give you compatible memory of the same type.
Yeah, so here's an example of how that would work in practice. So if you're, for instance, a compositor and want to render to a buffer and after display it on screen, you could query display constraints from KMS and then render constraints from OpenGL. Then you can take both of these constraint sets and merge them together, and you obtain a constraint set that is suitable for both. And you can, for instance, pass the merged constraint set to GBM to allocate a suitable buffer. So yeah, just a little more detailed example with some explicit constraint sets. If KMS says, I want buffers allocated in local video memory aligned to 1K, and OpenGL says, I want buffers aligned to 2K, then you can allocate with GBM buffers that are in local video memory and aligned to 2K, and both KMS and OpenGL will be happy.
Okay, so given that high-level design sort of as an initial goal, we worked through a bunch of case studies to build up our detailed requirements and to evolve the design, see if it held up under stress. So this first case study is the simplest case, more or less, that we started out with as sort of a base case. This is the problem of satisfying pitch alignment requirements for various devices. So people have probably seen bugs like this in the wild, where if you're doing something like prime render offload, you have multiple GPUs involved, and they might have different ideas of what the stride or pitch of the buffer that you're presenting should be. I have some examples here of some pitch alignment requirements from various vendors that we tried to dig up. Please take these with a grain of salt, because these were dug up at the last minute, and they're mostly for illustrative purposes. On NVIDIA hardware, I know that we have 32-byte alignment requirements for pitch if we're doing rendering or texturing, and 256-byte alignment if we're going to do display. AMD for display seems to require 256 bytes in practice. On Intel, it seems to have various cases. It can be as low as no alignment requirement or 1 byte alignment for some use cases, aligned to the bytes per pixel for other operations, and then it seems to be 64-byte alignment for a display. So if you want to, for example, render on an NVIDIA GPU and display on an Intel GPU, you have to agree on what the pitch is going to be. And then if you want to do texturing as well, like if you're in the typical use case of some kind of system compositor, you want to make sure all these operations work on some combination of those GPUs. So what you would do here is query a list of modifiers for each device, specifying the usage that you want to have available, and then intersect those modifiers. And this ends up being sort of trivial here because the only modifier you're going to get that works with all of these is going to be linear. Then for that linear modifier, you would need to query and merge the constraint sets from each API that you're using again. And again, at this step, you have to specify the usage over again. Because the modifier is derived from usage, but does not imply usage itself. There's a many-to-many relationship there. So the constraint set query and stuff needs to know what your usage is as well to be able to report the correct constraints. And then, as we saw earlier, merging for this type of constraint is relatively trivial. You just find the least common multiple of all the pitch alignment requirements and report that as the overall requirement.
We have a small question on IRC. It is unclear who does the merge call. Does it have to be the client allocating the buffer? Can it not be handled inside GBM, similar to graalloc?
It can be any component can do a merge. The result should be the same. If you pass in 3 different sets to the allocator and have them merge them, that's fine. But I think it makes the API easier if you only have to pass in 1 set across every API boundary. So I think anytime you have 2 sets available, you should probably merge them down to 1 and pass them around. But that doesn't really affect the design. I think it works either way. So a couple lessons from the first case study. This type of operation is applicable to any kind of minimum alignment requirement. So surface alignment, pitch alignment, width or height alignment requirements, anything like that. The same basic thing also generalizes to minimums and maximums just by replacing the merge operations with min and max. And it's also relatively simple to code up and visualize. I think most people understand how this works and the problem it solves. So it's a good example to start with, I think.
Okay. Another use case is local video memory. So some hardware like discrete NVIDIA display engines, they can only scan out from local video memory. So if you want to display something, you need to add this constraint. The naive solution will be to add the very simple constraint which just says, I want local video memory without any value. So there are a few problems with that. First problem is local to what? Because if you have 2 devices, a simple constraint that just says, I want the buffer to be local, it doesn't describe which local to which device. The second issue is that some devices have multiple local heaps. So if you say local, maybe the driver needs maybe the driver needs more granularity to know exactly where to allocate. So our solution is to add a new constraint, which is a heap constraint. And inside the heap constraint, you have a list of possible heap IDs. So the driver can say, I want the buffer to be allocated in heap A or heap B, and that's a constraint. So each device can expose multiple heap IDs. So GPU can have a local video memory and another type of local memory. We can namespace heap IDs by subsystem to prevent conflicts. For instance, we could have a namespace for DRM above heaps, another one for DRM. And merging 2 constraints, heap constraints, is just taking the intersection of the heap IDs. Yeah, so that works for both input constraint sets.
I mean, I guess what about the case of if you have like multiple sort of attributes on a heap, like if you have the ability to access system memory, but you might have a constraint that a particular engine needs to needs to scan out from uncached memory as opposed to cached.
Yeah.
I mean, I guess we could just bake that up as a separate heap, but
yeah. So yeah, it's still an open question. There are a lot of open questions in our proposal, and I think part of what you're saying is the second point in this slide. Maybe we need some kind of regular or shareable memory heap, or in general heaps that are universally recognized. And maybe we need to be careful about combinatorial explosion if you have a lot of flags. Maybe maybe we can come up with other constraints. Maybe not. Yeah, we need to discuss about this.
Yeah, I think a lot of that was
just
there was a talk about how to decide what is a heap and what isn't. I think at Linux Plumbers conference this year. And there's a lot of those questions, like, should the attributes be part of the heap? Should they be a separate thing? That separate thing might be another constraint that says I cannot do cache memory, for example. It's not really clear yet, but the idea of a heap ID seems like it's powerful, at least. So that's the starting point for our proposal.
If the heap ID is generic enough, it probably can work. The way that this is done in Vulkan is sort of a two-tier system. There's heaps and then there's types. And there's a mapping from types to heaps. And the types contain both the heap and properties like is it cached, etc. And so if you kind of map Vulkan types to these heaps, then it should be able to describe what you need by kind of baking it in. It does mean that you can no longer, for instance, figure out how much memory has been allocated from a given heap, because there might be some overlap in terms of the underlying allocations. But I don't see why we couldn't sort of bake that kind of information into the heap ID, as long as it's a driver controllable thing in some sense.
Yeah, and in some ways this is the generalization of the Vulkan mechanism to cross-device.
Yeah. So lots of things to still be discussed. Another thing we can see about this is that merging two constraint sets can fail because one device may say, I want local video memory to my device, and another device may want to say, I want local video memory for me, and then it doesn't work if we intersect both of them. But this makes sense because you cannot scan out from both at the same time. But yeah, just something to keep in mind. And yeah, we need to come up with a good deep heap ID mechanism. I think the discussion just right now is a good demonstration of this.
Another difficult problem we ran into was what to do with unknown constraints. So these happen by, as a property of the system we've defined. We have a design that disperses the constraint knowledge throughout the system components that you're using. So you're going to have a lot of system components talking together, and it's not realistic to have all of them version locked. At the most simple example, you have maybe an old kernel in the user space, or vice versa. But you might also have a mixture of Mesa drivers and proprietary drivers. You might have a mixture of old system compositors, like an old Wayland compositor, and a new application. Hopefully they're at least using the same version of the driver underneath, but they might not be. So at some point, you're going to have a component that will encounter a constraint that it's not aware of. And then the question is, what do you do then? So assuming you're the component that sees an unknown constraint, you can either ignore it, in which case you might still succeed allocation, but you might get something that's not actually compatible with the usage that was specified because you haven't accounted for all the constraints reported. That seems not great. The other option is to fail the merge or allocation. And this seems like it provides more robust behavior at first, but it can also fail in this corner case where you have these things that we refer to as implicit constraints that later become explicit. So let's walk through that in more detail here. Too far. So in this example, we have an implicit constraint of local video memory. So let's say in the current status quo, drivers use some kind of logic to place certain allocations in their device local video memory. It might be like when you think this might be something that's going to scan out, it ends up being placed in video memory implicitly. Then at some point, someone comes up with this design that says we should make a constraint for that. Let's make it explicitly specified by the usage whether or not you need to be in video memory. And so this is great. You update your allocator, you update your components that specify usage, so they all are aware of this explicit constraint. So now you only have memory placed in the device local video memory when you actually have a constraint saying that it needs to be placed there. The problem is that if you have an old allocator, or sorry, an old component reporting constraints, so it's not aware of this constraint and doesn't report it, mixed with an allocator that has been updated to use the new explicit constraint and hence won't place memory in device local memory unless it receives the constraint, you're going to have a bug. You're going to get memory that's not placed in the required memory location because the constraint wasn't specified. So that's probably bad. That means you're going to have, in the standard bug of new kernel regressing old user space probably.
I think what we learned from modifiers, obviously everything else worked perfectly well and there were no problems. But it's got to be do it with every single component, explicitly opting in or not at all and just go back to the old implicit world. So I'd say in that case, if you are moving to an explicit constraint on placement, then maybe you need to have everyone communicate down that the placement can be, universal or don't care or whatever, rather than trying to mix the two worlds.
Yeah, so that's what we came up with. We couldn't have something so granular as requiring you to opt in or out of constraints in general, because then you could never introduce a new constraint to the system. But yeah, rather than doing it on the granular basis of every single individual constraint, we've opted to propose that you have a versioning system for the constraints themselves. So for every different constraint that's introduced, it will have some implicitly associated version, which is basically an incrementing number in the file, the header that defines all the constraints, that is incremented whenever we have a new release or whenever a new one is added or something along those lines. So each version has each constraint has an implicit version. Additionally, to make sure everyone's on the same page, each constraint set contains a required special case constraint that reports the version of that constraint set. So anything that reports constraints will set that to its last known version, the version that it's aware of and using. And then when you merge constraint sets, the merge op for that type of constraint is take the minimum. Additionally, allocators and really anything else that operates on a constraint set, so this includes the merge library, the common merge code, will merge in their version when they perform that operation on the constraint set. And then the onus here is on the allocators to preserve their prior implicit constraints, basically what Daniel said, fall back to the behavior. If they see a constraint set that is less than the version of the explicit constraint that they're operating on. So if the allocator was updated to handle explicit requests for video memory and it saw that the constraint set was less than the version that added that constraint, then it would fall back to its old behavior and use heuristics or place everything in video memory. And once you have this, we reasoned out that you should be able to safely ignore constraints that you're not aware of, because it should result in, if everyone's following the rules, it should result in behavior no worse than before the constraint was introduced. In that you'll fall back to the heuristics or whatever it is. It might not be good behavior, but it won't be any worse than before. There won't be regressions.
So there's a question from IRC, quoting, if I understand correctly, to produce a list of acceptable heap IDs, you need to query the heaps that exist, right?
Potentially. If you don't somehow know them, yeah. There's a lot of, I'll probably save those questions for the workshop. There's going to be a lot of questions about heap IDs. I think, as I said, heap IDs is a large problem in and of itself. Back to the current case study here. The lessons we learned from this were that both backwards and forwards compatibility are important. If you don't have one, you really don't have either. And ignoring unknown constraints, as I said, should produce behavior no worse than using an older version of the component that was expressed in that constraint. So if you don't handle a given constraint, if you just ignore it, it should be no worse than if you hadn't upgraded whatever piece is reporting it.
Yeah, so we've now seen all of the high-level stuff. So we can maybe dive into the lower-level design proposal. Yeah, of course, all of this is subject to discussion, and the more low-level you get, the more you can get into bike shedding territory pretty quickly. So nothing's final. We can discuss. So in our proposal, constraint sets are variable length lists of 64-bit integers. The first list item is a header with a type and a size specified. So you have basically the header and then a certain number of items depending on the size, and then another header, and then and so on and so forth. The explicit length is necessary to skip unknown constraints, which is we want to do that with the versioning scheme we've seen just before. In our design, most constraints are vendor agnostic. Yeah, we've tried to come up with a solution which doesn't involve vendor-specific constraints, but maybe those are required somehow. This will complicate merging a little because we can't. It will be difficult to have a single merging function. Something that would further complicate the design will be to have fully opaque constraints. Yeah, we'll see. But the current proposal is to only have generic constraints. So we've implemented the merging logic and some helper functions in a sort of shared library. It's pretty small, but it needs a home, and it needs to be shared between the kernel and user space. Because both will use it. So the current proposal is to use a header-only library in kernel UAPI headers. Maybe it's not the best solution, but at least it's the simplest solution. We can discuss that later. We have no helpers to choose which allocator to use when doing the actual allocation. So we just recommend user space to guess and check, to just try, basically. So user space is already aware of all the DRM devices involved in the constraint negotiation. So user space can just try and listen them and until it works, basically.
So there's another question from IRC. Could the constraint version be simply the maximum known enum value?
The maximum known enum value?
Enum value, yeah.
I assume that means the maximum known type, if it's a...
Yeah. I mean, that sounds possible, yeah. It seems like a possible device, possible solution, because yeah, each time you add a new constraint, it increases the version, so that could be it, yeah.
And I think that's very similar to what Simon wrote up actually in the example code too, which we'll get to later.
Yeah, I just wrote it manually, I think, but yeah, right, I think the latest constraint number was the version number as well, so. Yeah, so here's an example of how this could work in EGL, for instance. So you'd use EGL to query rendering constraints, and so rendering is a little bit yeah, rendering and texturing. So we've introduced a new entry point, EGL query DMA constraints X, which will take a format, a modifier, and an external only flag, which is also used in the modifiers extension. Basically, more or less says whether it's for rendering or texturing. It's a little complicated than that, but with all of these inputs, the entry point could output a constraint set for this usage.
Like usual for Vulkan, it's a little more complicated there. The one line of code becomes several. The current thought is to extend VK get physical device image format properties to return constraints in addition to the other information it returns. It's not completely clear yet how that squares with the usage of that same function to report format modifiers. I think you might need to specify only one modifier per call and call it multiple times or something. That's not totally worked out yet. But basically, you get a constraint set out of usage you specified using that function, since it pretty much exactly specifies how you're going to create a Vulkan image. Additionally, we would have to extend the VK memory allocate info structure so you can allocate memory with a set of constraints applied to it. So that the struct is just another input struct to memory allocation that specifies all the constraints you want to use. We would also have to extend image creation. And one of the main reasons we have to do that is if you have something like that pitch alignment constraint we were talking about earlier, it's obviously going to affect the layout of the image, not just the type of memory allocated for it. So in order for the Vulkan implementation to be able to report memory requirements for like a pitch linear image properly, it's going to have to know what the pitch alignment requirements are. So they have to be passed in an image creation time too. And we thought about doing this the other way around, where you would just get constraint sets out of get memory requirements, or whatever that function is called. But then you have that chicken and egg problem where you create an image first, and then what's the pitch of that image, and then it reports the constraints, and those constraints might affect the image layout, and you're going in circles there. So that probably won't work that way around.
So another question from IRC. Isn't it a bit clunky to expect user space to just guess and try multiple times? Isn't it possible to give it something that's known to be good?
So that's, I mean, that's for the which device to allocate from, right? Yeah, I think the question is user space needs to guess the device where allocations must be made. Yeah, so it's a difficult question, and yeah, maybe we can come up with something, but we've not focused on solving this issue, and we've just said, yeah, let's fix everything else, and maybe even we can think about fixing this particular issue. And if you have something to add, James.
We haven't deferred it just because it's hard either. It seems like a lot of stuff is in flux here. Like it seems like there might be designs evolving in the kernel that might give us more options very soon, or it might be that the current designs are all we have. It also might be the case that constraints can themselves express the device that is required for allocation. It's not totally clear if that's a good design or not yet. So there's a lot of options here, and I think the problem sets don't necessarily intersect that much. I don't think solving that precludes solving the constraint problem.
All right.
Yeah.
Okay. Oh, are you going to say something, Jason?
Yeah. So one of the problems that kind of gets into this mess when it comes to specifying heaps as constraints and dealing with allocation on different specific GPUs, we have some hardware where there are modifiers that basically imply that it has to live on exactly that GPU, but other modifiers might allow it to be in system memory. And so if you're sitting in a multi-GPU setup, there may need to be some sort of a mechanism for saying, if you use this particular modifier, then you have to be on dev DRI code 1, and it has to be local memory there.
Okay, so that's a good...
So that's an example of the type of thing that we're likely to.
Yeah, that's also come up with logic, to be fair. Unfortunately, the only thing harder than naming and identifying heaps seems to be naming and identifying devices. So I don't have any good suggestions, to be honest. But at least you're not the only ones.
Yeah, and that's kind of why it was changed. I think in my older proposal it was device IDs instead, and now it's heap IDs because they, even though they're hard, they seem less hard. But yeah, maybe you could constrain that by saying you have to use that particular heap on that device, and that's just a proxy for that. But you could also have device IDs.
Yeah, depending on how heaps get advertised, if you're allowed to have heaps in the global list of all heaps that exist, that are implicitly tied to a particular device, then it probably can be specified simply as a heap constraint.
Yeah.
It kind of depends on what heap ID ends up meaning in the long
run.
Yeah,
I think that has to be true anyway, because there'll definitely be some kind of heaps which are unavailable to some kind of devices. If you have, say, a heap which is non-bar exposed, then that's not going to be useful for other devices. So I do like that idea of solving it with the heap ID and then tying particular heaps to device access.
Okay, we're getting short on time, so let's try to get through the rest of the slides here.
Okay. So yeah, let's talk about KMS. So to query display constraints, the natural solution is to ask KMS. So KMS is a little bit complicated because usage is kind of hard to describe. For instance, if you just want to display a buffer, it's fine. But if you want to rotate the buffer with the rotation property, maybe the constraints will be different for the buffer. And that's the case, for instance, with Intel hardware, I think. Maybe other hardware as well. So to be able to give constraint sets, KMS needs the whole KMS configuration for all CRTCs, planes, and everything like this. So in our proposal, KMS takes the whole KMS configuration plus the frame buffer width, height, format modifier. And with all of this information, it outputs a set of constraints that the buffer will need to be allocated with for this usage to be fine. So one possibility will be to make DRM mod addfb handle 0 BO handles as a special case. I think we've talked about this last year, but so calling addfb with 0 BO gives a fake frame buffer that can only be used for test-only commits. And if you use this frame buffer, it gives KMS information what is the width, height, format modifier. And then KMS could fill out FB constraints PTR blob property with a constraint set. There are a lot of questions. Maybe it would be better for userspace to be able to pass a list of potential modifiers to be used. So yeah, we still need to discuss about this.
Yeah, I'm going to jump past GBM. It's really simple. We add a constraint set to the existing call. And this is an example of the merge library. You're going to jump past this too. Sorry, Simon. But look at the link there. That's Simon's code. I want to make sure I got this slide up. Here's a link to our workshop. So obviously there's a lot of questions. Please come and join us for the workshop. We can discuss all the open questions there. I think we're mostly out of time for questions now. But also look at the next slide in here. This is a list of our references. This includes a detailed discussion. The entire email that Simon and I went through to come up with this design is archived there, unedited. So take a look at that as well if you have questions on how we came up with these ideas.
Okay, we are exactly on time, and thank you very much, folks, and we can continue that tomorrow during the workshop, right?
Yep.
Okay, thank you again, and see you.